Welcome to Analytic Methods for Lawyers. I'm Seth Chandler, professor at the University of Houston Law Center, and today we're going to be talking about Type 1 and Type 2 errors. Knowing that there are two types of errors is extremely important. It's good if you can remember which kind is Type 1 and which kind is Type 2, but what's more important than actually remembering the number is to understand the trade-offs that exist between type 1 and type 2 errors, as well as the cost of each form of error. So what I'm going to do in this essay, in this video, is to look at type 1 and type 2 errors, and I'm going to do so in a particular context, that of classification. So this is a little bit of a preview of work that we'll be continuing with when we study machine learning, but it's not intended to really do machine learning in detail. It's simply using it as a mechanism for understanding type 1 and type 2 error. We'll also be doing a little bit of statistical testing. With that, let's begin. Okay, the first thing we're going to do is to import some data. This is data that we'll be using again in this course. It's on recidivism. That is what happens when you let people out of prison. Do they get caught committing crimes, or do they abide by the law? And there's a pretty famous data set at this point from Florida, which looks at recidivism in certain counties. So we're going to import that data. That data will also be available to you on the course website. And we're going to get it. There it is. And as you can see, it has the names of the people, which we really don't care about here. I'm actually at this point going to use a magnification and make this a little bit smaller so it can fit in the video window here. And you can see as we go across that there are about 20 columns on this, most of which we don't need to understand, but there it all is. Okay, and do we have a little more? We have a little more. Yeah, okay. So let's take it back up to the top and to the top left. Okay, there's our data again. Now, what I want to do, and let me now go back to a more reasonable magnification, is to simplify the data a little bit. What I want to do is, first of all, I want to shuffle the data rows to make sure that they're not in any particular order. And then I just want data on the sex of the offender, the age, the race, their juvenile felony count, their juvenile misdemeanor count, their juvenile other counts, the number of priors they had, and then what we're trying to ultimately predict, which is their 2-year recidivism, whether they recidivate within 2 years of leaving prison. So I'm going to seed our random number generator so that this is replicable, and then get a sampling of the data. I'm then going to put that data in good shape here, creating training data and test data. And now I'm going to show you the data sets, just the first 5 rows of each. So here's our training data. We've got a 56-year-old male, Caucasian, no juvenile felonies, no juvenile misdemeanors, no juvenile other counts, but 7 priors, and 1 means they did in fact recidivate. Here's a 21-year-old male Hispanic, nothing, 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 and they did not recidivate. That's our data that we're going to train our learning algorithms on, and then we're going to see how it performs on the test data. So here's our 21-year-old male Caucasian who had a felony count, another count, a priors count, and he did end up recidivating. Let's now look at some classifiers on that data. And we're going to use a machine learning technique called logistic regression to develop a model that attempts to predict whether someone will recidivate or not. I don't need you at this point to worry about what logistic regression really is. Just treat it as a magical method that predicts, based on some data, whether someone will recidivate or not. So here we go. Bumpity dumpity dumpity. The machine is cluttering away. and it is getting close to done, and now it's done. And now it's produced a model, a classifier function, that when I use it can predict whether someone will recidivate or not. Maybe a corrections department might have this classifier and use it instead of a boring old hearing to determine whether to let someone go free. And again, we're going to study how these classifiers work later in the course. For right now, just treat it as magic. Okay, so we want to see how does our classifier perform on data that it's never seen before. After all, it could simply memorize the people that it saw before it, and then it could predict really well. What a classifier really should do is to predict well on data that is coming from the same kind of source that it was trained on, but where it had never seen the people before. So we're going to use the function called classifier measurements. The classifier we just built, see, CL, the test data, and we're going to try and predict 2-year recidivism. Again, do not worry about the syntax, just worry about the idea. And it produces something called a classifier measurements object. Okay, if we, give me one moment here just to see whether I do this in a little more detail below. I guess let's use this matrix here. What we have here is a confusion matrix for this classifier, and this is telling us, look, actually 1,208 people did not recidivate, 0, whereas 1,006 people did. We were able to predict 780 would recidivate, and we predicted 1,434 would not. Of those who did not, in fact, recidivate, we predicted 957 of the 1,208 would not, and these ones we got wrong. We said these people would recidivate when in fact they did not. We also got these people wrong. We said that these people would not recidivate when in fact they did. And we got these people correct. We said that they would recidivate, and they did. We'll take a look at the confusion matrix in more detail later in the course. But now let's talk about type 1 and type 2 error. Okay? For type 1 and type 2 error, you need to designate a positive class. And by designating one class as positive, you're basically designating the other class, possibly classes, as negative. And here, a positive class is what you're testing for. Here, I think we could test for either abidingness, the 0 value, or we could test for recidivism, the 1 value. Which one you pick as positive, it's somewhat arbitrary, but we got to pick something, so I'm going to pick recidivism as the positive class. If you flip the positive class, then you flip type 1 and type 2 error. So it's important when people, this is one of the reasons I'm not a huge fan of talking about type 1 and type 2 error. I'd much rather talk about false negatives, false positives, and specify what's the positive class. But in any event, a type 1 error is a false positive. This is where you think they're going to be positive, but in fact they are negative. So in these phrases, false positive, true negative, I like to start with the second word first. That's your prediction. Okay? It doesn't refer to reality. It's what you predicted. The first word is whether your prediction was correct or not. So a false positive is someone that you predicted would be positive. So if recidivism is the positive class, where's our false positive? It's someone that you predicted would be positive, but you got it wrong. It's false. Therefore, it's up here. Where's a false negative? Well, the negative refers to your guess, so it's up here. And it's false, so you got it wrong. So you thought it would be negative, but in fact it's positive. So 477 is the number of false negatives, okay? And a type 1 error is just a false positive. These are are type 1 errors. These are people we said would be positive, but in fact they're not. A type 2 error is our false negatives. You predicted that they would be negative, and they are not. There's a rather cheesy mnemonic in the written version of this video, which may help some of you, but let's just go through the picture again. I think that might be the best way. Look, if you put reality on the rows, as I like you to do, and your prediction in the columns, as I like you to do, and you put the positive class last, then type 1 errors are in the first row off diagonal, and type 2 errors are in the second row off diagonal. But another way to remember it is that it goes true negative, false positive, false negative, true positive. True negative, false positive, false negative, true positive. Okay? So in Wolfram language, by the way, once you have a classifier measurements object that we generated here, you can just ask it for the false positive number, and hopefully the false positive number, if 1 is the positive class, let's do it now, is 251. That's this number right here. That is the type 1 error. We can compute the type 2 error by asking for the false negative number. Type 2 error is false negative. Again, it depends which you designated the positive class to be. I'm going to designate the positive class to be 1, and therefore the false negative number, the type 2 error, is 477. Okay, so that number is, again, the one right up there. Okay, I want to look at the confusion matrix again. And here I've produced sort of my own cosmetic version of the confusion matrix, and I've used some color coding which may be helpful. I've colored kind of an olive here, the true negatives. I've colored red, the false positives. I've colored yellow, the false negatives, and I've colored green, sort of a yellowish green, the true positives. And here we've got reality on the rows and the classification in the columns. This is the convention that the Wolfram language uses. There's another school of thought which puts the classifications in the rows and the reality in the columns. They seem to be used about with equal frequency. I prefer this convention. The other thing I tend to do is to put my positive class at the bottom. Okay? But we can use this to read off those type 1 and type 2 errors. Type 1s are in the first row. They're this off-diagonal element, 251. Type 2 are in the second row, and this off-diagonal element, 477 here. Okay, now let's shift gears a little bit. Okay, let's look at how the classifier performed on a particular person. Okay, and let's take the first person in our data set. Seems to be a male, 21 Caucasian with 1 juvenile felony, 1 other juvenile count, 1 prior, and as it turns out, they did recidivate. So when the classifier looks at him, it magically determines, I think you're going to recidivate, okay? But that's somewhat of a shortcut for what's really going on inside the classifier. What's really going on inside the classifier is it's coming up with some probabilities. It's coming up basically with a categorical distribution over whether the person is going to recidivate or not and assigning probabilities. And it's saying the probability the person's going to recidivate is 0.603, and the probability that they're going to abide is 0.396759. So if we have a threshold of 50-50, this person is over the threshold for recidivism, and therefore the best prediction would be that they're going to recidivate. And so if we're using like a preponderance of the evidence standard, we would say that this person's going to recidivate. But there's no absolute requirement that we use a 50-50 standard. we could say that we're going to decide that we're going to act as if the person is going to be law-abiding unless we're 2/3 convinced that they're going to recidivate. We could have a 2/3 threshold. And if that were the case, then we would say, yeah, the probability is greater than half that they're going to recidivate, but we require 2/3, therefore we're going to classify them as an abider. And so long as that threshold is less than 0.603, we're going to say that they're going to recidivate. The moment it crosses the cusp of 0.603, then we're going to see that they're going to abide. And so for this person and for others, the choice of threshold, along with these probabilities, ends up determining their ultimate classification. And we can see this in this manipulate here. Let's just run it. Okay. And I've taken the first 25 people in our data set, person 1, person 2, person 3, 4, 5, 6, blah, 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 up to 25. I've set the threshold, and I've color-coded them according to both what they really end up doing and what our classifier predicts. So the default on person 1 was, remember, they're at about a 0.60 something, and in fact, they do recidivate, and we say they're going to recidivate because they're over the threshold. But if I move that threshold to the right, and now, as I moved it just, I went a little too fast there. No, I went a little too slow. There. As I moved the threshold over their probability, we flip their classification and say they don't meet the standard for classifying them as recidivating. We'll classify them as abiding, and I've noted the color change as a result. And so as I move this threshold, you're going to see people who actually do recidivate change their color from green to yellow. And for people who don't recidivate, who abide, you're going to see their color change from olive to red. Let's just watch that happen. As I move it all the way over, well, if I set the threshold this high, there's nobody I think is going to recidivate. If I say you got to be 98% certain, then no one's going to qualify, and everyone's going to be either olive, meaning we classify them as abide, and they do abide, or yellow, meaning we classify them as abide, but they do recidivate. And you'll notice that by setting the threshold very high, we have a pretty high number of false negatives here, of type 2 errors, whereas if I set the threshold very low, if I set it low enough, then now we're not saying anybody's going to abide by the law. Everyone's got some chance of recidivating, and so everyone's colored red or green, and now I have a fairly significant number of type 1 errors where I say that they're going to recidivate, but in fact they would abide, and so I'm ending up locking up people in prison when there's really no good reason to do so. And so by changing the threshold, I sort of create trade-offs between type 1 error and type 2 error. As I move the threshold to the right, as I increase the threshold, I start to increase type 2 error and decrease type 1 error. And as I move the threshold to the left, I decrease type 2 error and I increase type 1 error. Well, we can actually do this not just with the first 25 people. I just picked 25 here because otherwise I'd have too many bars to visualize. We can do it with the whole gang. And to do this, we've got a little bit of code here. We've got a resource function written by yours truly that really automates this process. And we can now see as I change the threshold, boom, 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 we can see that there's a trade-off. Here the threshold is very high. We have lots of type 2 errors, but we have no type 1 errors. Here the threshold is very low. We have lots of type 1 errors, but no type 2 errors. And here is the sort of intermediate positions. if we look at this graphic from the top, we can see that trade-off. Now I'm just looking at the same picture I was before, but I've shifted my angle of view. I could try to kind of do it manually here, kind of like that, but it's actually easier to do it programmatically, and so I just wrote some code to do it. And then if I just want to see it in 2 dimensions to begin with, there's some more code I have here that lets us see it in 2 dimensions to begin with, and there we go. You can see the trade-off between type 1 and type 2 error, okay? So by changing the threshold of classification, we alter the trade-off between type 1 and type 2 error, and the optimal point on this curve depends on the cost of a type 1 error and a type 2 error. If you think these people are going to go out and commit crimes, but you know, that's not so bad. Who cares about crime? But God forbid we should lock someone up for longer than they need to be. Well, we'd try to avoid type 2 errors, and I think we'd be down here. Whereas if we thought, you know, locking up for someone for longer than they really need to be, that's too bad, but it's not so awful. But crime, when they come out, oh my gosh, that's awful, then we might be up here. Okay? And obviously, if we had a balanced position, we might be more in here. Okay, so I just showed you type 1 and type 2 error in a classification setting, but it also exists in choosing significance levels for statistical testing. Suppose I have 3 numbers, and a null hypothesis says, you know, these numbers were drawn from N01, but there's an alternative hypothesis that says that they were drawn from N1.51. So let's use the mean of our draws as a test statistic. As I've told you, the mean is often a powerful test statistic. And let's compute the distribution of the mean of any 3 draws from a normal distribution. So we're going to do this here. Here's one normal distribution with a mean of mu and a standard deviation of sigma. Here's another identical normal distribution y. Here's another identical normal distribution z. And let's compute the mean of x, y, and z. And I'll just make sure the computer understands that the standard deviation has to be greater than 0. So if I do that, as it turns out, that is also a normal distribution with the same mean and a standard deviation equal to the standard deviation of the underlying distributions divided by the square root of 3. Okay? So now that I know that, I can figure out what is the distribution of the mean for if I'm drawing from N01 and its normal distribution 1 over the square root of 3. And if I'm drawing from N1.51, its normal distribution 1.5, 1 divided by the square root of 3. So if I plot the PDFs here, okay, we can see that the blue curve represents the distribution of the mean of 3 numbers drawn from N01, and the orangey line, or orangey curve, represents the distribution of the mean of 3 numbers drawn from N1.51. What I want to do now is to set alpha, and I want to set it at 0.1. That means I don't want a situation to occur in which the null hypothesis is true, but I reject it more than 10% of the time. Okay? I don't want a situation where I claim basically the null hypothesis is false, even though the null hypothesis is true, to occur more than 10% of the time. So to do that, I'm going to compute, if I set a value at x, what the rarer probability is of the blue distribution, the null distribution. And if I do that computation, I guess you saw the answer already. But if I do that computation, here's what I get. I get some complicated formula. But let's plug it in for letting that rarer probability be our alpha value of 0.1. And we're going to get two numbers, 0.949 on the high side and negative 0.949 on the low side. So we're going to set our critical values at negative 0.949 and positive 0.949. So if we look at this curve here, this blue curve, I've just taken our drawing before and I've added a purple vertical line at the high critical value and a green critical line at the, a green vertical line at the lower critical value. So the idea is that only if the null hypothesis is true, only 10% of the time will the number either be, the statistic either be to the right of the purple line or to the left of the green line, okay? So I've now set my alpha level, and by doing that, I've established my critical values. But what I've also done, you can see, by the way, that in this diagram here, you can see the red shaded area. If I get a number in one of these red shaded areas, even if the null hypothesis is true, I'm going to say that it's false. That's going to be a mistake. That's going to be a type 1 error. But there's also the possibility of a type 2 error here. That is, supposing the alternate hypothesis were true. Okay? By setting the critical value on this at this purple line, that would mean that anytime I got a statistic that was to the left of the critical line, I would be accepting the null hypothesis even though it's false. And I've colored that area yellow. And if you remember your definitions of CDFs, you'll remember that this area is just the CDF of the normal distribution at 1.51 evaluated at whatever that purple line number is. That, I guess it was 0.94 or so. And if we look up here, we can see that that number is 0.17. That fraction, 0.17, is our type 2 error. That's the probability that if the alternative hypothesis is true, we're going to reject it. And so you can see perhaps that the tougher I am on my alpha level, if I set my alpha level and I say I want it to be smaller than 0.1, that's going to swing the purple line over to the right. It's going to swing the green line over to the left. And that will, in fact, make the possibility of a type 1 error smaller. But by moving the purple line to the right, I'm going to increase basically the size of the yellow area, and that's going to increase the probability of the type 2 error. And so there is a trade-off between the type 1 error and the type 2 error, and you can see that in this set of graphics that I produced. Okay? It'll just take a moment. Let's take a look at those, and you can see what I've done here is I've specified a type 1 error, an acceptable type 1 error. Here it's 0.25. I've drawn the green and purple critical values. That in turn has led to the red shading of areas to the right of the purple critical value and to the left of the green critical value. But that purple line also lets us know what the beta, the type 2 error is, the yellow area. And you can see that as I decrease alpha and widen this area between the green and purple lines, I'm increasing beta until by the time I get to, I insist on a alpha of 0.001, I don't want to, I really don't want a type 1 error. There is a significant probability of a type 2 error. In fact, it's greater than 50%. It's greater than 75%. And so when you're doing hypothesis testing, this is the trade-off you make between type 1 error and type 2 errors, and whatever level of alpha you set is going to determine how that trade-off works.